Hello, I am Deniz Bashgoren.
And I am Cem Belentepe.
We implemented Conway's Game of Life in ARM assembly. This is a part of our project of emulator, ARM Cortex M0 emulator. And this is the second part in which we program a game, which is Game of Life, in ARM assembly. First of all, let's see what we built before moving on. As you see in this screen, we have cells which are colored and they change with time. And they create beautiful patterns. First of all, what is Game of Life? Game of Life is a cellular automaton. But what is a cellular automaton? A cellular automaton, it's a term from computation theory. A cellular automaton consists of cells, as we've seen in the previous slide. As you see, a cellular automaton can be in any size and it has cells. Every cell has a state. States can be different depending on the context. For example, we can have cells alive or dead. For example, we can represent the alive state as number 1 and dead state as number 0. So every cell would be either in 1 state or 0 state. The states change at every time step. That is, at t equals 0, we can have the state on the left side of the screen in which we have 5 living cells and 4 dead cells. And at t equals 1, that is, at the next step, we can have this state. That is, it can change. But how does the state change? Does it change randomly or does it change in different ways? No, it changes in predetermined deterministic ways. For example, in this example, we define the changes of the state as following. At every time step, the cell which had a state of 0 becomes 1, and which was 1 becomes 0.
The rules of Game of Life. Game of Life has 3 basic rules. Those are, the first one is any alive cell with 2 or 3 live neighborhoods will survive, such as this state. This point on the middle has 2 alive neighbors, so it will move on to the next state as it is before. Or any dead cell with 3 neighbors, 3 alive neighbors will become a live cell. For example, in this middle cell will become a live cell since it has 3 alive neighbors. And the other rule is all other live cells die in the next generation. Similarly, all other dead cells stay dead. So they will die in the other conditions. So
let's take a look at the code from top. We have 5 functions, which are init, draw, update, select random number, and pick color. First of all, we go to init. There we initialize the initial states, and then we move on to the game loop. In a game loop, first we go to draw function, in which draw function looks at the RAM, at the memory. It draws the cells depending on the state. Next up, we have update function. In the update function, we have our game logic, in which we change the states. And we don't reflect the changes to the screen yet, because update only changes the state. Next up, we branch back to the game loop, that is, we go back and then draw again. Thus, we have a game loop which repeats itself, that is, we first draw, update, draw, update, draw, update, like that. Now, we will move on to each function to describe the functions in detail.
So from now on, we will switch to the C code because assembly code is pretty hard to understand, and well, C code is easier to show in the screen. And our first part of the code is initialization, which will set all cells into a random starting position. A random algorithm we use is we just look up a random algorithm. It will use the overflow to generate a new number, actually, and it has a weird magic numbers. So if we multiply a seed number with a number and add to another number, it will create, and we will set it to the seed, and we can use the seed being positive or negative to our cell's initial position. Later, after the initialization function is finished, we will draw what in the scene. So it will just look up all the cells from its starting position. Cell start is just a number, which we use as a constant in our code, and it will have two for loops. And in this for loop, we will just look at all the grids in the scene. In that, we will have the row and column positions in pixel position of our grid. And later, we will use our pick color function to pick a color according to its state and the position in the scene. Later, we will put a 4x4 rectangle to our position, and we are multiplying by 5 because we want a one grid overflow, which is the background, and it's 0, to show as our grid frame. And then we will use the peripheral function and use the color row and color to set the color. And then we will increment our cells by 4 since it's a void pointer and we use as an integer. So when we increment by 4, it will just move on to the next position in the grid. And when all of them are done, we will use the peripheral refresh screen function or call to refresh our screen and show our drawings. In the update function, we have two parts, which is the first part is game logic and the second part is just a mem copy. The update, well, in the game logic part, we will have a cell start and next cell start as an array point, and then we will update the inner frame of the grid. So we will just look at from 1 to 47 instead of 0 to 48 and so on for the rows and columns. And using the game logic in the Conway's game of life, we will check all the neighbors. Since neighbors are in a linear array and they are in void pointer state, we will just move back and forth in our cells to get the 8 neighbors we will need. Those are the 8 neighbors. For example, this is the left top and this is the right bottom position. And later, using the state and the function, we will just change the next cell. For example, if the cell is alive and the neighbor is less than 2 or greater than 3, it will die. Or it's 0 and neighbor is 3, it will live on. And else it will just keep its state. And then we will increment our next cell and cell pointers to the next position. And we will do it in a 2x2 loops to the loop to work on each grid cell. And the mem copy will just copy all of the next cells into cell because, well, we need to keep moving on and the drawing function will move on from the cell. To just copy, we will just take the cell as a cell start and next to the next start, and until the cells end, we will just copy the values and move by 4.
For every cell in our cellular automation, we have only 2 cells, that is 1 which means alive and 0 which means dead. But what we did is we assigned a color to every state. That is, if the color, if the state is dead, that is, if the cell is dead, it will remain black. But if the cell is alive, we will color it depending on its position. The point here is that it's just for aesthetics. So how do we determine the color? Top left corner, the top left corner of the frame, will be in green color, and the bottom right corner of the frame would be in blue color. We're going to do a linear interpolation. That is, the colors will change depending on the distance from one corner to the other corner. Now let's analyze how colors change from green to blue. If you look at the green color, it has 0 red, 255 green, and 0 blue. If we go to the blue side, if we increment, we see that the blue part changes from 0 to 255, and the rest stay the same. So what we need to do is to change the 0 to 255 when we go from green to cyan. And from cyan to blue, the blue part stays the same, the red part stays the same, the green part goes from 255 to 0. Now let's take a look at a screenshot. We define x distance as distance from the green side to the blue side, and the y distance from top corner to the bottom corner. We have a predetermined window sizes, which are horizontal 320 and vertical 240. If we add them up, it makes a distance of 560. Now we want to interpolate the colors between green and blue onto distances 0 to 560. How do we do that? First of all, we start from green. We divide the parts into three parts. The first part is the greenish part, the second part is the cyanish part, and the third part is the blue part. As you see, when in the first part we go from 0 to 55, that is, we just increment by 1 at every step. We can map that directly to the distance. When we have 0 green, it can be a distance of 0. If we have distance of 1, then it would be green of 1. Thus, we go from 0 to 255 like that. Every pixel, every distance increments a pixel, color pixel by 1. Next up, we move on to the cyan part, in which we need to decrement from 255 to 0, and the distance keeps rising, so we need to make it 255 minus distance. When distance is 0, 255 minus distance makes 255. That is the cyan color, as we expected. And when we have a distance of 255, the green part becomes 0, and we reach to the blue part. So we need to decrement distance as we go further. And the last part is easy. We just keep it as a fixed color, which doesn't change anything because it's a small portion. We just keep it at blue. The color picker is a bit tricky. What we need to do is we need to set the R1 register, which in our C code represents the color. R1 register holds a value. It holds either 1 or 0. Now, if it's 0, we understand that it's a dead cell, and dead cells always become black, so we just return FF000000. It's black. Now, once that been returned from there, we understand that we need to color the cell because we eliminated the black cells. Now, we divide this into 3 parts. As I said, the green part, the cyan part, and the blue part. First, we calculate the distance, that is I plus j, just x distance and y distance, make up the total distance. Next up, we need to, first we pick the green part. It's the simplest one, after the blue one actually, but it's a simple one. In the green part, we have first FF fixed, that is the alpha color. The next 00 is the blue one, it is fixed. FF is green, which is fixed. 00 is the red part, which is fixed. FF is the blue part, which is fixed. And next two characters, which correspond to 8 bits, need to determine the green part, which will go from 0 to FF. So we have distance. Distance's first 8 bits determine the distance from 0 to 256. So we just shift by 8. Why do we shift by 8? When we shift by 8 to the right, the first 8 bits of the distance go away, and we only have the upper part of the distance. Now, after we shift by 8, if we have 0, that means that the distance was less than 256. So if distance is 0, we understand that distance was less than 256, and it corresponds to the green part of the coloring. So we just have a base address and add the distance, and thus we just get the final color. It's simple. Now we have shifted out the first 8 bits. We have only 2 bits left because the 9th bit corresponds to the values 256 to 512, and the next byte corresponds to values 512 to 560. We check those again by shifting, and we color the corresponding cell depending on our if statement. The blue part, which is at the top, at the very bottom, is very simple because it's a fixed color. And the tricky part is the cyan color, in which we need to create a 255 minus distance number, and then we need to shift it to the right place. To have 255 minus distance, what we can do is we can negate all the bits, that is from 1 to 0 and from 0 to 1. If we negate all the bits, it becomes a negative number. That's what we want, a negative number. Then we need to add 255 somehow. But if we, instead of adding 255, we add 256, it corresponds to just adding a 1 bit to the nth bit, setting 0 to 1. So if we eliminate that bit, that just corresponds to what we want. That is the bits 0 to 8. So we need to shift out that bit and other bits that become from 0 to 1. First, we shift 24 to the left. That way we have our 8 wanted bits on the very left corner. And then we shift it back by 16 so that it goes to the needed place, as we've seen in this by underscore signs. Once we've done that, we make an OR operation with the color bit sequence with our distance bit sequence. Thus, we finally place our bits in the needed places. John Conway was a mathematician, was a brilliant mathematician, whose most significant inventions are game of life and some others. He actually hates to be remembered this way, but it's the simplest and most brilliant invention that he made, other than his other complicated things. He unfortunately died this year due to coronavirus disease. So we tribute this slide and game to him. And that's it. The slide has come to an over. I was happy to make this slide. Thanks for watching and stay healthy.